Okay, everyone. Welcome to AIP Public Lecture Series. Myself, Dr. Ankit Kumar Mittal, and I am Journal Coordinator of AIP, and I am also working as Assistant Professor in Chandigarh University. So this is our public lecture series where we organize basic lectures on the research and topics related to bachelor and masters. So the Association of Indian Physicists is a subdivision of Janardhan Singh Foundation, which is registered under MCA Government of India. The main branch of AIP is in Barnala, Punjab, and we have divided this AIP to further 6 regions, that is North, South, East, West, Central, and Northeast Council. And our main objective of this association is to motivate the students, teachers who work in the uh, physics field. Further, our aims to innovate physics in teaching and theory and experiments. It introduced community to the various physics research field and allows them to learn from one another's research area. Many talented scholars wish to perform good research, but somewhere they need more facility or collaboration, and we will provide collaboration through this. To provide a meaningful scientific and academic discussion platform. So we are looking forward for the scholar faculty member to explore the interdisciplinary research work. So we have assigned a few peoples who are working at specific positions. So I'm not going to get you bored to read these names. Okay, you can go through our website, which is aipbharat.org. You can visit and find out more about it. So moving forward to today's talk. So our today's speaker is Dr. VISHNU CHAUHAN. He's assistant professor in Department of Physics at RAMJAS College, which is at University of Delhi. So Dr. VISHNU CHAUHAN has obtained his PhD from Guru Gobind Singh Indraprasth University, New Delhi, and with collaboration with IUSC New Delhi. He has also worked as a RA in IUSC New Delhi. Further, he has worked with Indo-German Science Technology. He's also PDIF at GSI in Germany. Now, I would like to invite Tishum Tan, who is our newly joined technical member. He has obtained his BTech from Madan Mohan Malviya University of Technology from Gorakhpur. Apart from his BTech academics, he has interest also in physics. That's why he has joined our association. So welcome to Tishum. Kylie, are you there?
Yes.
Yes.
Uh,
Yes.
Hello, everyone. I'm. It's an honor to be here, and I'm looking forward to contributing to this very noble association. Thank you.
So now I'd like to invite Dr. Vishnu Chauhan. Kindly, sir, give us talk and
Thank you
please.
so much, Ankit ji. And first of all, let me share my presentation.
Yes.
One moment, please.
So student, if you have any questions in between, you can type your question in the chat box. We will take your questions after the talk.
Is it audible to you, sir? Or
Yeah, you are.
my presentation
Vishnu
is
sir,
visible to
you are
all?
audible to me.
And what about the presentation?
Your PPT, yes, it's visible to us now.
It's visible now?
Yes, yes.
Okay. Thank you so much, Ankit ji. And I'm very much thankful to the president and other onboard members to the Association of Indian Physicists that gave me precious time to introduce something or a little bit about the material science, and that is basically for the bachelor's and master's students. So today's topic is topic is all about the metal oxide based nanostructures, and how do we synthesize the metal oxide nanostructure, and that how these nanostructures lead to the applications. This is the view of the university that I am working as assistant professor in RAMJAS College, University of the Delhi. The upper view is the main university campus, vice chancellor residence, not residence, office, and the lower picture, that is our RAMJAS College, beautiful picture. So we start from the classification of the materials. Generally, we divide the materials into categories: metal and non-metals. Further, we have the further classification all about the metals. That metals are classified in two categories: ferrous and non-ferrous. Generally, you might be aware with the ferrous metals that those are the metals having the iron as their main constituents. And these can be cast iron, it can be alloy cast iron, wrought iron, steel, and alloy steel. Non-ferrous metals, these are the metals which have uh, their constituents other than the irons. It might be copper, aluminum, brass, tin, and zinc. In case of the non-metals, you have three categories: ceramics, polymers, and composite. Ceramics, these are the materials made from the clay that has been that high temperature to create their materials in form of hard or as per their properties. Generally, ceramics are brittle, hard, strong, durable, inert, and have high melting point. So they can withstand a lot of heat and can be used in the glass, windows, pottery, tiles, and many more things. Second, we have the polymers. The polymers are generally divided into two categories: natural polymers and synthetic polymers. Natural polymers that are like silk, wool, cellulose, protein, and natural rubbers. Second, we have the synthetic polymers. These are the polymers that are made by the human activities or by some process. These are like nylon, polyester, Teflon, PVC, and others. Next, we have the composite materials. Composite material, generally, what is that? It's a combination of two material having the different physical and chemical properties, and when they are combined together, they create a material that is used for some particular application. Next, we have the oxides. Classification of oxides. We have four types of oxides: acidic, basic, amphoteric, and neutral oxide. In case of acidic oxides, we have carbon dioxide, sulfur dioxide, nitrogen dioxide. These oxides react with alkalines that form the salts. Second, basic oxide. These basic oxide are sodium oxide, calcium oxide, potassium oxide, magnesium oxide, copper oxide. These are the oxides that react with the acids and form the salts. Next, we have the amphoteric oxide. These amphoteric oxide are generally metal with the oxygen atoms: aluminum oxide, zinc oxide, titanium oxide, and other oxide. And these react with the alkali and acids to form salt. Next, we have the neutral oxides. These are oxides you are very familiar: hydrogen dioxide, carbon dioxide, and nitrogen oxide that do not react with both alkyls and acids. These are the important metal oxides. We have aluminum oxide, have the various application: magnesium oxide, calcium oxide, iron oxide, nickel oxide, zirconium oxide, hafnium oxide, silicon oxide. So I can say these are the oxides that generally these days are being worked a lot from basic application to the advanced applications. And what is the beauty of the oxides? They have the very high melting point. As per the specification or particular application, they are being used, that we will discuss. Further, we have the different metal oxides: noble metals, metal oxides, metal sulfide, and other materials. If we talk about the metal oxides, indium oxide, zinc oxide, tin oxide, titanium oxide. We have noble metals like gold, silver, platinum. We have metal sulfides, zinc sulfide, tungsten sulfide. We have other materials also like graphene and RGO. Mainly, what are the nanomaterials? What is the basic classification? Then what is the further classification? So nanomaterials, these are substances that are being reduced in the range of 1 nanometer to 100 nanometer. And on the basis of dimension, these are divided into 3: 0 dimension, 1 dimension, 2 dimension, 3 dimension. Generally, what are the 0 dimension? These are the nanoparticles, or in form of nanospheres, in form of quantum dots or nanoclusters. 1 dimension, these nanomaterials are found in form of nanorods, nanotubes, and nanowires. 2 dimension, nanofilms, nanolayer, and nanocoatings. And what about the 3 dimension nanomaterials? These 3 dimension nanomaterials are the materials that are found in form of multi-nanolayers, nanotube bundles, and nanoprisms. Here we can clearly see in the 0 dimension, we have core shell nanoparticles, we have encapsulated nanoparticles, we have composite nanoparticles. The size of these nanoparticles, generally in case of 0 dimension, is very, very less. That cannot be measured. Or 1 dimension nanomaterials, we can see in form of carbon nanotubes, carbon nanowires, or composite nanowires. Then in case of 2D nanomaterials, we have graphene-based composite materials in form of layers. We have carbon-coated nanoplates, and we have carbon-coated nanowells also. 3-dimension nanomaterials, that are mesoporous composite electrode materials. We have microporous composite electrodes, and we have the 3D structure of the electrodes. We can clearly see. So first, before we go for the synthesis of any kind of material, first of all, we have to know its properties. Then, on the basis of the properties, how these nanomaterials can be used for the further applications. So if we talk about the different properties, we have chemical properties. The metal oxide nanostructures can be ionic, covalent, basic, or amphoteric. Metal oxide nanoparticles or nanostructures have the different mechanical properties. It can be insulating, these can be semiconductor, these can be metallic, superconducting, ferroelectric, pyroelectric, piezoelectric, ferromagnetic, and multiferric. Optical properties, we have nanoparticles show their optical properties like UV absorption and the specific color absorption in visible range. We have photoluminescence also. Thermal properties, metal oxide nanostructures are very good thermal, and they are like for very good thermal conductivities. We have the very good surface properties as well. As I showed you that we have the well-defined crystal structure, surface property that brings the different semiconductors. Nanomaterials are the biocompatible. Little bit we start from the application. We have the very good environmental remediation applications that nanoparticles or nanostructures play a key role in the environmental remediation. What is the environmental remediation? It's a process of removing the pollution or contamination from the water or soil that our human health can be protected, or they can remove or break down the harmful chemicals. The metal oxide nanostructures are used in form of energy storage devices. They are used for the catalysis and the solar cell conversion process, organic synthesis. There are some other industrial applications as well. They are used in electronics, energy productions, textile, food industry, pharmaceuticals, cosmetic, and wound healing, tissue engineering. There are certain complex metal oxides where 2 or more than 2 metal oxides are combined together or synthesized together. They form the complex metal oxides. They have like particular applications that includes the photocatalysis, transparent conductive materials, supercapacitors, battery components, photoelectrochemical water splitting. Further, next we have the these materials are very good materials. Like you might be aware about the titanium oxide, zinc oxide, or iron oxide, aluminum oxide. They have very good applications. Like they are being used in our daily life. Like titanium oxide are used sunscreen, cosmetics. Right? Titanium oxide also used pharmaceuticals and pigments, food additives. Zinc oxide has a number of applications here. Like a few we can very few applications are there. Like we can use zinc oxide in paints, pigments, sunscreen, cosmetics. Further, we have aluminum oxide, cerium oxide, copper oxide. They have also the specific application. How the metal oxides appears and what are the colors of the metal oxide. So here are some examples. Like if we talk about the aluminum oxide, we have aluminum oxide appear in form of white color like a salt. We have cobalt oxide. We have titanium oxide is also crystal white. Carbon nanotubes appear in form of black colors. Copper oxide, we have some reddish color. Gold, you all are very familiar with the gold. We have the cerium oxide, iron oxide, and aluminum oxide. That is also white in color. Magnesium oxide, white in color. Zinc oxide is also white in color. We have silver. Silver appears, silver nanoparticle powders appear in form of silver. So if we talk about the synthesis, mainly broadly, we have the two approaches for the synthesis of the metal oxide nanostructures. The broad approach, that is top-down, and bottom approach, and their detail or explanation is clear from its name only. The top-down approach is the approach that involves the breaking down large pieces of the material into smaller pieces, and it is a physical method that can avoid nanoparticle solvent contamination. But in this process, we require a high amount of energy that can cause damage to the process patterns. Next, we have the bottom-up approach. This approach involves the single atoms, assembling of single atoms and molecules into larger atoms or nanostructures. So it is a biological method that becoming more common, is eco-friendly, cost-effective, has a wide range of applications. So here we can see in the top-down method, we have a big material, or we can say the bulk material. The bulk material is reduced into the small materials, small pieces that is appear in form of powder. We can clearly see here. Further, if we go for the further process in top-down method, then we can achieve, simply we can get the nanoparticles. In the bottom-up approach, it's a quite reverse process to the top-down approach. Initially, we have the atoms or molecules. These atoms combine together, forms in form of cluster. Further, these combine together, we can have nanoparticles. There are some techniques for synthesis of the nanoparticles. We have top-down approach, bottom-up approach. We have categorized here what techniques includes in the top-down approach, what techniques include in the bottom-up approach. In top-down approach, for instance, we have ball milling, thermal evaporation, laser ablation, sputtering. Bottom-up approach includes CVD, hydrothermal, co-precipitation, and sol gel method. These are the very simple techniques, can be used in a very very small space. Further, we have other application, our other technique also, including the previous techniques: ball milling, sputtering, atomic layer deposition, physical vapor deposition, molecular beam epitaxy, sol gel, chemical vapor deposition, co-precipitation, thermal decomposition, thermothermal, microwave assisted deposition, hydrothermal synthesis, inert gas condensation, laser ablation, electron beam evaporation, pulse layer deposition. We have the number of techniques for the synthesis of the nanostructures, but all the techniques cannot be applied for a particular material. We have to look for the properties of the material. We have to look for what application we will use. Basis on the properties and basis on the application, we choose the technique, then we further process for the synthesis of the nanostructures. Here, if I discuss about this is the very this is physical technique, and this is radio frequency sputtering techniques. It uses the sputtering process. It involves that this technique involves the changing into the electrical potential of the current in vacuum environment at some radio frequency, that to avoid the charge building up to certain type of sputtering target material. In this technique, that the plasma is obtained, and the plasma is obtained and the target material is appeared into the form of droplet, and that further it comes to the anode, and in form of like small particular atoms sputter and form at the anode in thin films. So in the picture we can see at the on the upside we have the negative power source, we have cathode, we have a target plate, that is the target it is made of some particular material that we want to make the thin films from that material. Suppose we have the titanium oxide, so this target material or this is used in form of pellet, a big pellet. So this is the target material. We have the anode, and just above the anode we have the substrate. We just stick the substrate just above the anode, and we can see the like last blue, or we can see in between there is a plasma. So there is a formation of the plasma. We have the ionized gas also. We have neutralized gas for the to complete the process. So overall, what happens in the process? The target atom sputtered from the cathode, and that stick or come to the substrate atom. Further, we in a short time we just get the thin film. Other, we have the chemical technique. It's very simple technique, can be used in a small room also, small space also, that requires very less equipments, but that is specific or particular on the basis of the properties of the material. So we have the co-precipitation technique, that is here I'm just taking the example to synthesize the copper tin hydroxide. Initially, we have taken the two substrate, copper chloride or tin chloride, we mix together, and then we took 2 mole of sodium hydroxide, added to 20 ml water, stirred together at some optimized temperature for few minutes. Here we have taken the 180 minutes. Further, we got the solution. The solution is dried for at 80 degrees Celsius for 8 hours. Then we got the powder, synthesized powder. But the synthesized powder is not ready to use. Further, we have to process it, and it is calcinated at some particular temperature for 400 degrees Celsius for 3 hours. And the calcination, further we have to calcinate it at the higher temperature. Then we get finally we get the copper tin hydroxide. So initially, before synthesis of any material, just we have to optimize at what temperature we have to calcinate our material, for how much time it will take to calcinate, and like how much time what shape of the material, spherical, nanoparticle, or other shape, like what shape we will obtain. Once we have synthesized the material, we have to analyze, like what are the properties of the material, what are the structural properties, what are the chemical properties, and what are the optical properties. So for analyzing all these properties of the material, we have some characterization techniques. We have FTIR, we have PL, photoluminescence, we have HRTEM, we have VSM, we have BEAT, we have XRD, we have AFM, XPS, HRSM, UV, TG, EDS. All these are the basic characterization techniques, gives the information about the structural, morphological, optical, chemical, mechanical, and other properties of the materials. Why we use the metal oxide nanostructures as a nano composite? There are some reasons. Large surface to volume ratio we have good optical properties, surface plasma response, quantum size effects. Like little bit about the characterization techniques. Why the SAM is used? Like this is the technique, use a specimen of the electrode accelerated electron beam that record the signals and result into the results from the interaction between the beam and specimen that provides us a particular image of the particular portion of the material. Then we can see, or we can say that these nanoparticles in spherical form or in cluster form or in any flower form or any kind of other form, like we obtain. We have transmission electron microscopy that is used to characterize the size, crystallinity, phase, growth, and direction of the film. We have AFM technique that is used to characterize physical surface properties of the materials. The important property we have initially, we have XRD, X-ray diffractometer, that gives the information about the crystallinity of the material. Optical microscopy, it it gives visualization about the UV visible spectroscopy and ellipsometry. Raman spectroscopy, we can know about it gives information about the vibrational fingerprints, or what kind of metal we have, what kind of material we have, or it gives so many structural information also another. Here we have taken the example for some characterization techniques that will allow us to identify what particular characterization technique is used for. Here we have the same images. You can see very clear images obtained using the after synthesis the metal oxide nanostructure. We have to know what shape we have obtained, what is the size of the nanostructures. So here we can see the A micrographs, we have the nanorods, very small nanorods we have. In the B, we have the nano husk. We can see the distorted cubes in the image C. And if we go for the further analysis, we can see in the image D, we have the porous spheres. Next, we have the self-oriented flowers. We can see in the F image, the beautiful flowers are appears. So on the basis of the same characterization techniques, we come to know which shape do our nanomaterials or nanoparticles have. Further, the advanced characterization techniques beyond the SEM, we have TEM, transition electron microscopy. So we're taking the example here, we can see we have obtained the octapod shape of uniform nanomaterials. So in the B image, we can clearly see, like here we can see the image of single nanoparticle. So how advanced it is from the same image. Further, if we go for the more analysis, we can obtain the lattice parameters also. We can determine like which plane do we have. We have the 2 to 0 plane, and the specific interspacing distance between the molecules. Here we can obtain, like we can see here, we do have the 0.29 nanometers. So we can say like how specific or how deep analysis we obtain from the time micrographs. We can rotate the material in any form, any angle, in minus 20 degree, minus 10 degree, 0, 10, 20, or any like. This is very basic characterization technique, I must say. Just after the synthesis of the material, first of all, we go for the X-ray diffraction study. Initially, it provides you what structure you have obtained in your material. We have the different structure of the materials. On the basis of the structure or on the basis of the XRD patterns, we can obtain the crystallite size of the material. Here we see we have two materials, copper oxide and nickel oxide. We obtain the different peaks for the copper oxide and nickel oxide. On the basis of the different peaks, we come to know that these peaks are of face-centered cubic nanostructures. How do we come to know? These are the face-center. We have the standard data file. That these standard data file we call JCPDS XRD data. This JCPDS XRD data is matched with our provided data. If all the peaks are well suited or well matched, we can say this is particularly of this structure. Here, like we can say we have the face-centered cubic structure of copper oxide and nickel oxide nanoparticles. On the basis of the FWHM and the intensity of the particular peak, we measure the crystallite size. We have the Scherer formula to determine the crystallite size. So on the basis of using that formula, we can determine the size of the nanoparticles. Further, earlier we talked about the SAM. Here we are talking about the AFM. There is a little bit difference, but the spectroscopy is entirely different. In the SAM images, we get only black and white images. Here we can see the colorful imaging. One more beauty of the AFM image, that here we can get the 3D structure of the image or 3D structure of the nanoparticles. On the left hand side, we can see we have the 3D structure of our nanoparticles. Here we have taken the example of copper oxide thin films. We can clearly see the 3D structures how the nanoparticles are agglomerated, how some nanoparticles are not agglomerated. With the beauty of the 3D images, here we can easily obtain the surface roughness of the material. How rough is the material? We have root mean square roughness, and we have average roughness, we have other roughness also. As well, we can obtain here the 2D image of the metal oxide nanostructure. So here we can see we have obtained the micrograph of different temperature. On the basis of different temperature, we can see the morphology, that it changes a little bit. Next, we go to the optical properties. To determine the optical spectra, we have absorbance. On the basis of absorbance, we can determine the transmission as well. On the basis of transmission or absorbance spectra, we can determine the optical band gap of the material. On the basis of the optical band gap, we can decide, or we can say, like, in which category our material do we lie. Is it insulator? Is it semiconductor? Or it is conductor? So generally, here we have taken the energy band gap of the chromium oxide nanoparticles. We can see that these different peaks are taken on the variation of the different annealing temperature or calcination temperature. The chromium oxide nanoparticles calcined with the different temperature. On the basis of the different temperature, we can see like the optical band gap that increased from approximately 3 electron volt to 3.1 or 3.2 electron volt. So there is a slight variation on the basis of the calcination temperature. So optical study allow us to determine the optical band gap, to determine the absorbance, to determine the transmission of the material. Further, we can determine the thickness of the material using the ellipsometry technique. So there are some metal oxides have some specific band gap. Zinc oxide, it is generally 3.4 electron volt. Iron oxide, magnesium oxide, tungsten oxide, zirconium oxide, that is very high band gap. You can see like it's a 5 electron volt. So generally it is used as a dielectric, and zirconium oxide, on the basis of this band gap, we can use zirconium oxide in the memory devices as well. So particularly Dr. Ankit has worked on zirconium oxide. It's a very, very good material, and he has done very excellent work on that. Next, we have the titanium oxide, cerium oxide, magnesium oxide, iron oxide, and other material. So these, the value of the band gap are not particularly strict to the value that I am telling. On the basis of the synthesis process, on the basis of the technique, particular technique you are using, on the basis of the different parameters, the band gap may vary slightly. But we can say that we can come to know in which category it will lie. Either it would be semiconductor, or it would be insulator, or it would be dielectric. Further, we have the Raman spectroscopy. Here we have taken the example of vanadium pentoxide. Similarly, there is some doping of some other material, 5%, 10%, 20%. On the basis of the dopant, the Raman peaks slightly changes, but not completely. We have different peaks. In case of 5%, it's quite different. In case of 10%, it's quite different. In case of 20%, quite different. So here we can see the dopant change the structure of the material as well. At the 20%, we can see that there are the number of peaks. It means the crystallinity increase in the material. The structure that improved on the basis of the doping. So generally, Raman spectroscopy, we can say, can be used to analyze metal oxide in materials like catalysis, minerals, corrosion, and films. Raman spectra can give the information about the identification of pigment, corrosion process, surface treatment, characterization of amorphous material or nano crystalline phase, characterization of heterogeneous catalysis. Further, like this is only the small example. Particularly like metal oxide are being used for the memory devices also. Here we are discussing resistive switching memory device. What is the beauty of the metal oxides? Simply, metal oxides have the numerous applications. In memory devices, these days we are getting the very good response of the metal oxide memory devices. Alternative to the, if the material have the very high dielectric, they are very good for the memory devices. Here we can say this is the structure. The structure is the switching memory device has the structure is very simple. It's MIM. The lower metal M is means lower metal, I means insulator, and upper M is another metal contact. So here in the A graph we can see substrate, then dielectric, metal, then dielectric, then metal. Or simply we can see here in the another graph also, we have the back contact, we have the substrate, then we have the high K, then we have the aluminum gate. It's a top electrode. And there are the other examples also we can see here. So generally, oxide-based resistive switching memory, MIM capacitor for the silicon analog circuit we used, and on the basis of the MIM structure that are used for the dynamic random access memory also, and the MOS structure also. If we change the in-between layer, if we take other oxide material, and we use for the other electronic circuits extensively, we can use in the space or nuclear and other memory military applications. We do have the hafnium oxide is a promising for MOSFET, generally due to only the high dielectric material also. We have metal oxide semiconductor, FET, and also can be used in the non-volatile flash memories. If we talk about the applications of the metal oxides, nanostructures, we have numerous applications as we discussed. We have nanoparticles, can be used as catalysts, paints, medicines, semiconductors, electronics, packaging, biosensor, cosmetic, bioengineering, dye sensitized solar cells, automobiles, nanofabrics. Further, we have other applications of the metal oxides, microbial activity, absorbent, semiconductor, gas sensors, ceramics, superconductor catalysis. So generally, we can say first we choose the material. We go to the properties of the material. On the basis of property, we select the synthesis route of the material. Then we conclude that this particular material or the synthesized material will be used for such applications. Here we can see like we have the numerous other applications also, and metal oxides are used for the enamels, for this beautification of so many things. They are used in medical devices for the target drug delivery and cancer treatment and other applications also. They are being used for LEDs, cosmetics, and other luminescence materials, oxide coatings, memory devices, as I discussed, supercapacitors. We have the fertilizers as well. Zinc oxide is also used as a fertilizer. Energy efficient materials, high reflectivity mirrors, catalysis, the fuel cell, and dentistry. Metal oxides are used. Generally, zirconium oxide is a very good material because it is stabilized at high temperature and it has a very hard material. That's why it's used in dentistry. Textile industry, we are used in the crop protection also. And generally the high temperature materials are used for the gemstones, for making the ceramics, and chemical and biosensors, antimicrobial activity. We have the laser mirrors also. We have the electronics, all are also used in electronic devices. We have the zirconium balls. These zirconium balls are very hard and be used to crush the materials in between. We have anti-corrosion coatings, or further metal oxides can be used for batteries, wastewater treatments, color filters, drugs, and additives. Further, specifically, if we talk about the medical applications, we have taken the example of iron oxide. The iron oxide, we can say, is a have been used for the fluorescence imaging, MRA contrast agent. These are used for the antibacterial activity, wound dressing, targeted drug delivery due to the if we make the nanoparticles in the specific range or less than nanometer, we can cure for the targeted drug delivery. Other we can go for the sensing systems, biofilm preventions. In dentistry, we use many nanoparticles like gold, copper, silver, carbon nanotubes, iron nanoparticles, titanium nanoparticles, zinc nanoparticles. These nanoparticles are used in dentistry. Other metal oxide based nanoparticles are used for the photoelectrodes. We have the ceramics as well for so many purposes. There are some references, and thank you so much for listening.
That was a fantastic talk, Dr. Vishnu sir. So we
Thank you so much,
really
ma'am.
enjoyed your talk. So you started from the basics of metal synthesis and discussed about different techniques and talked about different characterization technique also. So I really enjoyed your talk. So we have few queries in the
Thank you,
chat
sir.
box. So I'm going to read one by one for you. You can also see by yourself.
Sure, sir.
So first of all, Mr. Ayush Paul has asked, in slide 5, you said that nanoparticles are biocompatible, but nanoparticles like Ag,
Yes,
TiO2, Ag nanoparticles, CNT, and CD-based quantum dots, etc., are biotoxic in nature.
right. So what exactly want to ask?
So he
These
is
are the
saying
numerous applications.
you are saying that these materials, you said that these materials are biocompatible, but
Yes,
quantum dots are biotoxic in nature.
actually, all the materials are not biocompatible, and all are not biotoxic. Depend upon that which approach we are using. Like if we use the zinc oxide nanoparticles, okay. After the synthesis of zinc oxide nanoparticles, we have to go for the further synthesis process that is called the green synthesis. In that green synthesis, we have to mix up other materials that makes the material that are biocompatible. Like we mix the turmeric, and sometimes we mix the cannabis. So these are some herbs that are used or mixed with the metal oxides that makes them biocompatible for the specific particular applications, like for the drug delivery or antibacterial activity. So we have to go for the green synthesis.
Okay. Hope Ayush is clear to you. Okay. Next question is from our founder chairman, Dr. Sanjay Kumar Singh. So he's asking, sir, please throw some light on the quantum size effect.
Quantum size effect, generally the application vary from the size of the nanoparticles. Generally, we say the quantum size of the nanoparticles is in the range of 1 to 10 nanometer, but it is very hard to obtain using the particular approach or particular technique. We come to obtain the quantum dots, and the quantum dots generally go for the particular applications. Like in case of the bio applications, we prefer the synthesis of quantum dots only, because the specific pore size of the skin is in the few nano range only. So with using the with this particular size only, we can go to the targeted drug delivery. Further, if we increase the size of the nanoparticles, we go to the 10 nanometer, more than 10 nanometers, like 100 nanometers, or more than 100 nanometers. So the application of the quantum application of the nanomaterials varies. For example, if I take the 50 nanometer thin films in case of the memory devices as an oxide layer, so the response of the oxide layer or response of the device, I have personally worked on that. the response of the device is quite good. If I go for the for 100 nanometer or 200 nanometer, the response is quite decreased because of the transportation of the ions. That is due to the transportation of the ions. So with the variation of the particle size, beginning from the quantum dots to the micrometer size, the application changes. Right.
Okay. Yes. So next question is from Mr. Kundan Sharma. So he's asking, is it possible we can get only one peak in the XRD observation?
That is also possible, depend upon the original structure of the material. If sometimes we have the mixing of polymer material with some oxide material, so that we get only broad peak. If it is polymer, that it is broad peak, and there are some other materials also that consist only one peak or two peaks. So that we have to see to the original data, how many peaks are there, how many structures are there. So it is possible.
Yes, I want to add something to this answer. So when we were pairing thin films on the silicon substrate, so I used to do the XRD of silicon substrate also. So that
Great.
shows a single peak at 57.3 because it has only a single crystal that is 101, that is only in one orientation.
Right.
So that we can get only single peak also. So next question is from Dr. Sanjay sir. How you isolated a single nanoparticle?
Only single nanoparticle?
Yes.
How do we accelerate?
Isolate, differentiate, how we take
Okay,
single
differentiate
nanoparticle.
single. It is quite complicated to differentiate single nanoparticle, but if the process is very fine or very optimized, we can obtain the single nanoparticle. If there is no agglomeration of the nanoparticles, it is quite easy to identify. But I can say like the chemical technique would prefer to isolate the single nanoparticles. But for that, we have to optimize our synthesis process many times. And like I would recommend TAM is the best characterization technique to analyze the single nanoparticle. So
Okay.
totally, sir, it depends upon the process like we are using, or depends upon the parameters, how much we optimize our parameters.
So next question is from Kundan Sharma. So he's asking, in AFM, what is the role of temperature variation?
In particular AFM, that I must say, there is for studying any kind of material or any kind of variation in material, like we can say we have the doping of the other material in one material, we have the temperature variation, we have the pH variation, and we have other variations also. So in AFM, like it can give the better image, or sometimes it can reduce the charge effect. If there is a reduce in the charge effect, we can say that we can obtain the clear image, clear AFM image. Similarly, we see in the SAM also, if there is a charging, we go for some temperature, or we can see if there is a temperature enabled with that, then we can get the clear images. But as I understand, we go for the journal at room temperature. I showed the image of the temperature variation. That temperature variation is for the material only, not for the AFM technique. That the person who used who synthesized the material, he saw the variation of the temperature, not in the AFM. So it was the materials property, not the AFM property. It was the variation of the material only.
Okay. So next question is from Dr. Vinay Kumar Sahu. So he's also one of the prominent member of AIP, and he's currently in assistant professor in Odisha. So he is asking, what kind of information can we obtain for heterojunction from UV visible spectroscopy?
From heterojunction UV visible spectroscopy.
Yes.
Sir, I must say, like for the heterojunction, I don't have like more idea about that. But we can say generally we can basic information we can obtain, like we can obtain the transmission, how much the material is transmitted. We can obtain the absorbance and further the band gap also.
Okay. So next question is from Dr. Vinay Sahu also. So he's asking, can we expect Raman spectra from metal?
Raman spectra from metal, yes, we can obtain the Raman spectra from the metal.
So you have shown them from for metal oxide only, I think, in the PPT. So
no,
in
the
lieu of
title,
that.
the title is focused on the metal oxides only.
Yes,
But
yes, yes.
we can go for the simple metals also.
So
And for the pure
Vinay
metals,
sir, and any specific doubts you have? So kindly unmute yourself and let's have some discussion.
Yeah, thank you, Vishnu sir, for this wonderful talk. Yeah, I
Thank
was
you
just
so much,
wondering,
sir.
can we see some Raman spectra from metal, only metal like gold, silver, metal oxide? We do see. So that was what was my doubt. Like gold, silver, like if you take only gold nanoparticle, silver nanoparticle, you sputter a gold thin film. So
Right,
that
sir.
is, yeah.
As per my knowledge, sir, we can have the Raman spectra for the pure metal, but I have worked only with the oxides or nanocomposites, so I have the more information about that.
Okay, sir. Okay, sir. Thank you.
Yeah, thank you, sir.
So we have plenty of more questions. So kindly bear with us. So next question is from Preeti Das. Sir, can you please explain about the size estimation of quantum dots from UV visible spectroscopy?
From the UV visible spectroscopy, it is very hard to determine, or I can say we cannot determine from the UV visible spectroscopy. But for the size determination, we can go for the TEM, we can go for the SAM, or we can also get the precise information from XRD as well. Or there's another technique, ellipsometry. We can go from that also.
So there is one information. Kindly stay for the group photo. We are going to take one group photo at the last. So
Sure.
The one more doubt from Suraj Kulkarni. So he's asking how to do dielectric study of metal oxide.
Dielectric study of the metal oxide. First, we have to choose the metal oxide, and the metal oxide generally it must be in the range of 3 to 5, or if it is more than 3, if it is more than 5 electron volt, then it is well suited for the dielectric study. So generally is based on the band gap.
Sir,
Okay.
can we do the TDR for metal oxide?
TDR.
Yes, sir.
Hello. Are you
Yes,
asking
sir.
about the TDR?
Yes, sir.
I'm not sure about that TDR, but we can
Okay.
go for the dielectric measurement. First, we can have the idea from the band gap, then further we can get from the dielectric measurement, and then further like we can go for the device fabrication.
Sir, can you suggest some reference book for the study of dielectric about the metal oxide? Is there any?
Sure. I do have the book. I can send to Ankit ji. You can contact him.
Sir, can I mail you? Gmail you?
Sure. I can
Okay.
send
Thank
you.
you
No
so much.
issue.
So Mr. Suraj, I am going to put the email ID of Dr. Vishnu sir in the chat box, so you can take it from there. So you can mail him.
No.
Okay, so you can get in touch with the Dr. Vishnu sir over the mail.
Thank you, sir.
Okay. So next question is from Miss Nikita Singh. So she's a MSc student and doing very good research in dye synthesized solar cell. So her question is, can you explore more on bottom up method? Which instrument are used in this case?
Bottom up method, I already explained that I can further go for that. No issue. Bottom approach is what? Here, like we have the small particles, we mix together and then we just get the particle in form of nanorings. Or if we say the top-down approach, we took the big particle, means the bigger particle break into the smaller particle. Here we take the smaller particles. Okay, then the further process go to the cluster, then for the nanoparticles. So we have the many techniques. For the bottom approach, we have the co-precipitation. It's generally the very simple technique. We have sol gel also. So for the beginning of if you are the beginner, you can try from the sol gel or co-precipitation method. That does not require so many things. And for further, you can go for hydrothermal and other technique also.
Okay. So next question is from Amrit Sagar. So he's
Mhm.
asking, please summarize some of the current research going on in this domain. What are some nice achievement in the field of recent year? Please explain for UG student level.
Okay, very good. Like if we talk about the material science, I have shown the various metal oxides. These are the current metal oxides like aluminum oxide, titanium oxide, tungsten oxide, and zinc oxide is very old material. And we have magnesium oxide. So all these are the materials. Generally, these materials can be used in form of pure metals, pure oxides like magnesium oxide, or if we mix other materials with these metal oxides, like we can say the dopants. So these come to the form of composite, and on the basis of the process of synthesis, we can go for the nanocomposite. We can make the thin films of these metal oxides as well, or metal oxide nanocomposite as well. So in bulk form or in thin films, these synthesized material can be used for the various applications. Further, as currently, like we can say the current areas, we are focusing on the energy storage devices. We are focusing on the supercapacitors. Water splitting is a very hot topic. Very good research is going on, and that is environmental remediation. As I told, that removal of the contamination from the soil and the water. It's a very good current research is going on the devices, on the photovoltaic cells, or on the solar cell. And the very current topic, that is perovskites material, are used for the various application, but there is a feedback for the perovskites material. There is a lead in most of the perovskites, but lead-free perovskites material are being used currently because of their efficiency is less. But the lead containing perovskites have the more efficiency, but they are not good for the human body. That's why the current research includes all these topics.
Okay, that was the fantastic answer. So let's move to next question. So Mr. Ayushpal is asking, can atomic AFM does not destroy the nanostructure since it directly make contact
Very
with the
good question.
sample?
Very good question. Actually, AFM works in 2 or 3 modes: contact mode or non-contact mode. That on the basis of the property of the material, the mode is chosen. For the oxides, that is non-contact mode is chosen. There's a bit difference between the surface of the material and the needle of the material. So the electron beam passes through the material. So we say there is no harm to the material if we use the AFM characterization technique.
Yes, this is the basic question, I think.
Basic question, very basic
yes,
question. Actually,
yes,
it goes in tapping and non-tapping mode.
Yes. So it is required to know earlier about the different method before proceeding for this characterization technique.
No
Yes.
issue.
Yes. So next, so I'm speaking the bigger question. I'm now, as we are out of time. So next question is, can we make metal oxide from graphene?
We can make the composite.
Yes.
We can make the graphene oxide as well, and we can make the composite with the graphene oxide.
Okay. Next question is, Amrit Sagar, is there any theoretical research on nanomaterials? Can you mention some nice sources to get in about these theoretical
Yes,
studies?
there is a theoretical study like this. There is a DFT, density function theory. In DFT, we use the theoretical simulation. Like there is existing work on, as I was telling, there is existing work on the band gap. So if we take some data, the reported data, and using that data, we make there are some Fermi energy levels, or we can come to know how exact the theoretical data gives information about the band gap. So density function theorem is there for the theoretical study, and there is another study that is COMSOL, that is generally used for in memory devices enabled metal oxides. So there are some these COMSOL and DFT theoretical studies.
Okay. So next question is, why different shapes are shown by same metal oxide as shown in TEM micrograph of iron oxide?
It depends for what application we are going to approach. Simply, if I have to make the thin films, or if I have to make some sensor, then I will go for the thin films. If I have to study some like dosimetry application, I have to go for the bulk material also. So it vary from application to application. Generally, the synthesis technique is chosen on the basis of application we are targeting. So on the basis of that synthesis technique, the size of the particular material may vary.
So next, there are two more questions. So next question is from Ayush Pal. So he's asking, what is the difference between dimensions of the unit cell obtained from XRD and crystallized size obtained from Scherer formula?
XRD and Scherer formula, I must say Scherer formula is for XRD only. If there is a variation in the crystallite size or particle size from other technique, that is considerable, but from the from XRD only, we use in XRD we use the Scherer formula, or for determining the particle size or crystallite size from the XRD, there is no other thing I can say. So there is no another way to determine from XRD. So Scherer formula is a very simple, or we can also use the William-Hall's method also is out there. But in William-Hall's method, we take the average of the many peaks, like many sharp peak. But in Scherer formula, we can go for the particular peak. So that is the thing.
So can you please explain about the characterization technique using TGA?
TGA.
Yes.
TGA, DTA, that I have never used, but I have heard about that. That is used for the hardness or some porosity to determine in the material. Or I think you can, sir, you can explain more better in TGA.
Yes. So I have done the work on TGA and DTA. So in this study, we will study the effect of material with the temperature effect. So we keep the material in the furnace or in some application, and we started increasing the temperature, and along with that we started measuring the energy and the mass of the particle. So how mass is changing with temperature and how much energy is releasing, is the energy is exothermic or endothermic, and based upon that we make the study. So like for my material zirconium dioxide, so after 700 degrees Celsius, there is no change in mass or there is very less change in energy. So we can say that above 700 degrees Celsius, my material is stable. So TGA is basically,
because zirconium oxide is already in a very high temperature level, no?
yes.
That's why it's hard to get some variation in zirconium oxide.
So there is one question I skipped. So it is from Dr. Om Tripathi. So
Mhm.
he's asking, can you please comment on possibility of building individual nanoparticles using quantum-based computer? So he's further adding, having single particle controlling would be great leap for coherent control and quantum computing.
It is very complicated question, I must say. It generally the formation of a single particle is very much optimized process. So it depends upon the particular process it can go with.
Yes.
No, I just asked like,
Mhm.
I mean, I really asked that. Is it possible to build, because for quantum computers, at least most of the techniques are based on single particles.
Right,
So
sir.
if you have single trapped ions or single
Mhm.
atoms, this is pretty much hard.
Right.
So you just told that it is actually possible somehow, up to some extent,
Right.
that you can get this single nanoparticle. So those
Right, sir.
nanoparticles, I assume that they're pretty much quantum objects. So
Mhm.
is it possible to make a quantum computer based on that? Because if you somehow can control, I mean, nobody had did any research on that.
Sir, making a single nanoparticle is it might be possible, but on the basis of like a single nanoparticle based quantum computer, that I cannot comment on that. Like theoretician can give good information about that because they have a
Yeah,
very good
no.
simulation and they have good idea.
Like pure experimentally,
Uh,
you uh,
formation in case of like can be possible or with the single structure only.
I mean, if you have 10 nanoparticles,
10 nanometer.
2
Obtaining the
centimeter apart, then you
Mhm.
can try doing a quantum information processing, isn't it? That is.
Obtaining the 10 nanometer is possible. There is no doubt, sir.
No,
For the
I'm not even asking 10 nanometer, 10 centimeter apart each. It
okay,
is.
10 centimeter apart each. That
This is
I
how
cannot
you.
comment more about that, sir.
Okay,
Because
okay.
this is particular with the person working with the catalysis or person working with the with some fluorescence technique. They can comment more about that because they have a very sharp structure and they can clearly see their particles if they are working with the fluorescence.
Okay. Thanks.
So now we're going to have a group photo session. So I request everyone to kindly keep their camera on. Just for 2 minutes, kindly keep your camera on with smiling faces so that we can have your photo. Kindly, yes.
I really do not have a camera on my computer,
Ankit
but
ji, no,
Not an issue.
Ankit ji, no one can have a more smiling than you. You are always smiling.
Thank you so much, sir. Sir, I think you got a professor look now.
You
Yeah.
may say.
Okay, I'm done with the photo.
Thank you.
Now I request Sanjay sir to say a few words.
Yeah, thank you, Dr. Ankit sir. I really enjoyed lecture delivered by Dr. विष्णु sir. बहुत ही बेसिक्स से स्टार्ट किए जो कि हमारे ऑडियंस के लिए बहुत ही यूजफुल है क्योंकि इसमें मतलब अंडर ग्रेजुएट पोस्ट ग्रेजुएट पीएचडी स्कॉलर्स भी हैं और
Thank
उनके
you,
लिए
sir.
बहुत ही बेनिफिशियल रहा. सो थैंक यू सो मच डॉक्टर विष्णु सर. आई होप ही विल also deliver lecture in future in our EIP platform.
Sure,
I
sir.
really appreciate your contribution for our EIP. Thank you so much, sir.
Thank you, sir.
Over to Ankit, sir.
Yes, thank you, sir. Sir, shall we give an appreciation letter now?
Yeah, you may
Yes,
proceed.
yes. अगर आप परमिशन दे तो मैं शेयर कर देता हूँ.
Sure.
So we will officially send this appreciation letter to you by email. But
Thank you so much.
just because we are doing it online, so let's do it. Let give the certificate by online way. So
Yes,
here is
yeah.
your appreciation letter. Thank you so much. So we are very much thankful
My
to you.
pleasure, sir. My pleasure.
Yes.
I have been trying to contact you many times, but by this platform, like I could see you, sir.
Yes.